So hello, welcome to our final 11th week class. This is probably lesson 22, I think, unless we missed a day. Did we miss a day at all? Did a day go by where we didn't have class or something like that? Anyone know? Anyone remember?
Tuesday.
Huh?
Tuesday.
Oh, we had a test, right? All right. One we cutting a class short would still be a class, but if we didn't have class on Tuesday, then this would be the 21st, I guess. And we're going to start by answering a few homework questions. So let's open up chapter 21. Let me start sharing my screen. And let's look at chapter 21. Right, is that what it was? Oh, what did I just close? That's horrible. The thing was there and I clicked it. Right as I clicked it, it X'd out. Unbelievable. Chapter 21, number 8, chapter 21, number 4, chapter 21, number 3b, chapter 21, number 1. Looks like chapter 21, we got lots of questions. So as we do this, I can't do them all, but oh, that's a practice quiz. If I answer a question that's similar to whatever question you have, just let me. Oh my God, that's a lot of information. Let's see. Studies have shown that mildly obese people spend less time standing and walking on the average than lean people. Is there a significant difference between the mean times the two groups spend lying down? So we have group 1 are the first 10. Those are the lean people. And then we have 10 more. Those are the obese people. We have time spent standing, walking, time spent sitting, time spent lying down. And we want to see, is there a significant difference between the average times the two groups spend lying down? So we don't care about stand, walk, and sit. We're looking at lying down. So is there a difference? So this is a not equal to null hypothesis, alternative hypothesis. Are they not equal? Where the null hypothesis is, of course, always equality, where they are equal. Are they equal or not? Well, let's check. Let's test the null hypothesis that they're equal versus the alternative that they're not. Are the conditions for inference met? Well, what are the conditions for inference? Well, we need SRSs and we need normality. So did they say anywhere? Well, they don't really give us that information, which is kind of weird. I guess you just kind of assume they are, or maybe this question was coming from somewhere else, but I don't know where that information is not here, so that's kind of weird. That is kind of weird. But anyways, let's go to Crunch It. So let's see what Crunch It shows us. It's got all the information. So this is a statistics test. This is a 2-sample t-test, right? They're not paired because there's 10 people here and 10 completely different people here. So there's no connection between them. It's not like left hand, right hands before, after. There's no pairing up. So it's a 2-sample test where we do not know the standard deviation. So we use T. And our first sample grouped group by group, right? Group by group. So you have group 1 and then you have group 2. So let's group by group. Group 1s are the 1s and group 2s are the 2s. The data we're going to use is the lying down data. We're not pooling them because we don't have that information. The null hypothesis says it's 0 and the alternative is 2-sided, and we calculate. Does that make sense? In terms of how to do it?
It does. I just had trouble doing the standard error.
So remember what standard error is. Standard error.
Like I did the numbers, but they always came out wrong, and I don't know how if I used the correct numbers.
Well, what's the formula for standard error?
S1 squared divided by n, and then plus S2 squared divided by n2.
All right. Well, let's calculate it. 52.04 squared divided by 10. And the other one is 46.59 squared divided by 10. We're going to add these two numbers, and we're then going to take the square root of what I got. And I get 22.0878. Or 0879, I meant. So it looks like, I mean, that's what I got. 22.08798, so 0880. It's fairly close. Probably because those numbers of 52.04 and 46.59 were rounded, which is why their numbers are a little different than mine. Does that make sense? Yes, no, maybe so.
It does. Thank you.
I mean, I don't know what you did wrong, but I just did it in my calculator and I got the answer. Fair enough? Fair enough. Okay, and then there was question 2 was also 21. So which one? 4 was next. Number 3B. Someone says 3B. Let's practice. Why do I keep doing that? 21. 3B. 21 3B says businesses know that customers often respond to background music. Do they also respond to odors? One study of this question took place in a small pizza restaurant in France on 2 Saturday evenings in May. On one of these evenings, a relaxing lavender odor was spread through the restaurant. On the other, no scent was used. The data gives a time in minutes that 2 samples of 30 customers spent in the restaurant and the amount they spent in euros. So when there was no order, they spent this many minutes and spent this much dollars or euros and so on and so on. Okay. Oh, wow, it's a lot of data. The 2 evenings were comparable in many ways, so we are willing to regard the data as independent SRSs from spring Saturday evenings at this restaurant. So they're giving us that SRS information. Therefore, at this stage, it will be, the authors say, therefore, at this stage, it will be impossible to generalize the results to other restaurants. Oh, the authors say, okay, that's just part of that, what we're giving. So does a lavender odor encourage customers to stay longer in the restaurant? Okay, so you did part A. So let's look at part B. Does the lavender odor encourage customers to spend more time in the restaurant? Examine the spending data. In what ways do these data deviate from normality? Well, let's look at the spending data. Let's go to crunch it. And let's look at a distribution. Let's look at a histogram. No, I don't want this. Let's look at graphics, histogram. And we're going to look at the what are these labels? Min. What is this problem again? Minutes and odor. Okay, minutes and euro spent for euros for no odor. Okay. So we want to compare euros spent for no odor and lavender. So we're looking at these 2 columns, euro no and euro lavender. So let's form a histogram for each one. This will be the euro no. And let's just form a histogram for the euro no. Does that look normal to you? That's not horrible. All right, it goes up, it comes down. It's a little longer on this side. Let's do one for, what's the other one? Your skewed a little to the right, yeah, a little to the right. Your oh, well, that's certainly not normal. Okay, that's certainly not normal. So when it says, how do they differ from normality? So there are two clear asymmetrical peaks in each distribution. Well, I certainly see two asymmetrical peaks in this one. Did I miss it in the other one? In the euro? No. Well, kind of hard to see that one. Maybe the sample size was the wrong size. The distributions are skewed and have many gaps. Well, we certainly saw that. We certainly saw that for the second one, but I'm not sure about the first one so much. Oh. I don't want a sandwich. It's not fair. Anyways, was that your question? Because, yeah, it's a little hard to answer because while these are true in the second one, I really didn't see them to be true in the first one. The only way I can really maybe see that is if I change the the bin size. So in the first one, which is the euro no one, you know, if I make it, let's say 10 bins instead of 5, you know, so maybe I'll see something like that. But, you know, how would you know to do that? So it's really a hard question to answer. The other one, you know, popped up immediately, but this one may be a little hard to answer. Does that answer your question about that one? Okay. And the other ones who had questions, were those questions possibly addressed? Whatever questions you might have had. Similar questions, or are there still people who want me to go over something? Today will be a lazy day. We'll go over things if you have to. I mean, if there's questions. Chapter 21, number 8. Oh, okay. A research firm supplies manufacturers with estimates of the sales of their products from samples of stores. Marketing managers often look at the sales estimates and ignore sampling error. An SRS of 50 stores this month showed mean sales of 41 units of a particular appliance with a standard deviation of 11 units. During the same month last year, an SRS at 52 stores gave mean sales of 38 units of the same appliances with a standard deviation of 13 units. An increase from 38 to 41 is a rise of 7.9%. The marketing manager is happy because sales are up 7.9%. Yay. Give a 95% confidence interval for the difference in mean numbers. Okay, a 95% confidence interval. I can do that. Statistics. We don't have Z, so we go to T, and we go 2 samples, right? Because there's the first SRS and the second SRS. And we're going to go to summarized because we don't have the data itself. So what do we have? 50 stores in the first one with a sample mean, 40. So a sample mean of 41. How do we know Z? What's the giveaway? Because we were not given the standard deviations. When you're not given the standard deviations, you use T. That's the giveaway. I mean, the sample standard deviations were given, but we weren't given the population standard deviations. What's, oh yeah, okay. So that's 11. And the other one was 52, 38, 13, 52, 38, 13. We're not pooling. We don't know they're the same. We want a confidence interval, and we want a 95% confidence interval. Calculate. So negative 1.725 to 7.725. So these are fairly close, but interestingly enough, they're not exactly the same. 50, 41, 11, 50, 41, 11, 52, 38, 13. Uh, 95%. Well, I wonder what would happen if we pool. Let's try it again with pooling and see what happens. T2 sample summarized. This time let's pool and see what happens. Negative 1.740 to 7.740. No, it doesn't help. It's weird. That's very strange. That's very strange. The only thing I can think of is maybe they're not using the computerized version of. Remember the degrees of freedom? We had a very complicated formula versus a simple formula. What's a simple formula instead of using the complicated formula? Anyone recall what that was? The simple formula?
With n-1?
It's the smaller of them minus 1, right? So Jaden says that's what I kept getting. Hold on, I'm copying his chat. That's what I kept covering, and the kid said it was wrong. Yeah, the only thing I can think of is that they want us to use 49 degrees of freedom instead. The problem is that you can't do that on Crunch It manually because it automatically does it. So let's try the following. T calculator. T calculator, T confidence interval calculator. Two samples. See, even here, it's going to use, doesn't allow us to input degrees of freedom ourselves. I don't know. I mean, I do know that if you have smaller degrees of freedom, it widens. So the fact that their numbers are bigger than our numbers lead me to guess that that's what they did, but I don't know for sure. But I mean, this should be the answer. So if everyone got it wrong, don't worry. The grades will be adjusted at the end of the semester. Explain in language that the manager can understand why he cannot be confident that sales rose by 7.9%. And in fact may have dropped. Well, notice that this interval contains not just positive numbers, but also negative numbers. Which means since we don't know where we are in this interval, it's just as likely to be in here, closer to negative 1.8, as it is to be close to 7.8. As such, maybe it did drop. I don't know. In fact, because this interval contains negative numbers right here, it's possible that it went down. It's just the numbers. So yeah, so Jaden said that's the numbers he got. That's the numbers I got. Can we do number 2? Oh yeah. Do women and men differ in how they perceive their life expectancy? A researcher asked a sample of men and women and to indicate their life expectancy. This was compared with values from actuarial tables, and the relative percent difference was computed. Perceived life expectancy minus life expectancy was divided from actuarial tables was divided by life expectancy from actuarial tables and converted to a percent. The relative percent differences for all men and women over the age of 70 in the sample are given. So these are our samples. To access the complete data set, okay, so you don't have to do it because they already did it for us, which was so nice of them. We see that it's a null hypothesis is that there's no difference, and the alternative is that it's a difference, which means it's a two-sided test. And we see that the difference of means was this, and the t-statistic was here, and our p-value. At the end of the day, it's the p-value that really matters. Our p-value was 0.05. So the mean for 19.5, I guess it's right here. And women's 12.71. These are negative because they went down. But at the end of the day, so it's just asking you for yeah, remember the standard error formula, the same one we had on the board a few minutes ago. And what percent of the time under repeated sampling would a more extreme difference have occurred? How often will we get something further than our t-statistic? That's exactly what the p-value gives you, that 5.281% of the time you will get a value past what we actually got. That's too often for me to reject the null hypothesis, and therefore I do not reject the null hypothesis, which is not what they asked for. Anywho, all right, we are 40 minutes in. We spent a lot of time on preliminary work and whatnot. I'm going to stop sharing for a second. I'm going to check my email just to see if how many people contacted me like I asked about the grades. I see 1, I see 2, I see 3, I see 4. So
do you want it on Canvas email or your other email?
well, Canvas goes to this one, and you can go directly to this one. And in both cases, I got 4. 2 of them from Canvas and 2 of them straight. I can, 2 of them from Canvas and 2 of them straight. I also have my Yahoo email, which people use sometimes, but nobody sent it to that one. I also have a Gmail email. I'm not even sure if you have that one or not. So I have they're all over the place. And if you do it after class, that's fine too. Someone just said, "Oh, we'll do it later." That's cool. Cool. Knock yourself out and have a good time. But we should keep going. So where are we? I think last time we used some 3 Canvas emails. Yeah, okay. So we had switched to the slides, correct? That was this class?
Yes.
Yeah.
Yeah, okay. So let me find them here. Close a bunch of emails and stuff so I can find them easier. Okay. CSUD, Canvas. Okay. Canvas. All right. Courses. And this is Math 140 Common Resource Sites. Okay. So last time we were doing what, 21? Did we finish 21? 22? 23? What the hell are we up to? Come on, you guys know better than I do. I forget things. I have no memory. Let's take a look at the 24th PDF. See if it looks familiar. No, 21. So 21 is comparing 2 means. Have we compared 2 means yet? We finished 22. Okay, wonderful. Okay, 22. So 23. All right, I'm gonna start sharing my screen again. Inference on two population proportions. Did we do this one? Maybe not. Okay. No, I don't think we did. Okay, so inference on two population proportions. Okay. We did one proportion, we did one mean, we're doing two proportions and two means. So this is inference on two population proportions by Ali Al-Sharaka, my boss, or at least my superior. So we know that p hat represents the proportion of successes, p hat equals x over n, but now we have two populations, two samples, two number of successes, two success or sample proportions. So we're just going to label everything with subscripts: p1 and 1, p1 hat, p2 and 2, p2 hat. Everything is your standard subscript. An SRS of size n1 from population 1 with a proportion of successes p1, and an independent, a completely separate SRS of size n2 from population 2 with proportion of successes p2. They must be independent for the math behind the scenes to work, so they can't be dependent. If they're connected, sometimes it might be a matched pair situation, which we have our own technique for. But if we want to use this chapter's technique, they have to be independent. And we want to compare, for example, the effectivenesses of treatment 1 versus treatment 2. And what are we going to use? Well, we have the proportion of successes in the first one. We have the proportion of successes in the second one. What are we going to do? We're going to compare the proportions. It's the easiest way. So when comparing proportions from two populations, we do inference about A, P1 minus P2, B, P1 hat minus P2 hat, C, P1 plus P2, and D, P1 hat plus P2 hat. We haven't done this in a while. Our good old-fashioned waiting for me to ask, and then everyone's shutting out the answer. That's like, you should let us out so you can test your brand new TV. I bet the graphics are fire. That's my new TV. It's kind of hard to see. Oh, let's see if I turn the light off. Hold on. Oh, wow. So where'd it go? Oh, there it is. Oh, so it's harder to see. But yeah, the graphics are fire, whatever the hell that means. Fire. I don't know. Fire. Talk English, man. Talk English. House tour. So, yeah, lifestyles of the not rich and not famous coming up. Okay, so A, B, C, or D, when we compare proportions, do we do it about P1 minus P2, P1 hat minus P2 hat, P1 plus P2, or P1 hat plus P2 hat? I don't know what the hell Megamind is, but right now I'm looking for A, B, C, or D. 1, 2, 3, go. Nobody's going. Oh, there they are. Okay. Go, everyone. Come on. The best movie, please. The best movie. Yeah, I'm talking about. The best movie. Best movie. Oh, excuse me. Well, let's see what we got. We got lots of A's. Got some B's. Got a C. People talking about movies. Megaminds. Megaminds. I don't know what that is. Megamind. All right. So when comparing proportions from two populations, we do inference about. Well, we're certainly curious. Oh my God. Oh. Well, yeah, I just threw up my mouth a little bit. So we do inference. We're trying to determine something about P1 minus P2, the true difference of proportions. But we're using P1 hat and P2 hat. We're using our actual sample proportions. And so this word about, I really don't like this word about. What does that mean? We use P1 hat minus 2 hats to infer something about P1 minus P2. So what does about mean? My guess is he meant B. Let's take a look. Oh, I was wrong. A. Okay. I didn't understand his note. I don't understand why about means that. But we're certainly using P1 hat minus P2 hats to infer something about, about. Okay, well, there you go. To infer something about P1 minus P2. But we don't do inference about it. I don't know. It's a bad notation, but hopefully you understand the difference between the hats, which is what we use, and the non-hats, which is what we're looking to find. So quick question. In an SRS of 103 male and 100 female college students, 61 males and 51 females said that they usually speed on interstate highways by 10 miles per hour or more. And the other people are all lying. But anyways, what is P1 hat minus P2 hat in this example? All right, I just used my calculator because I was too lazy to do it in my head. Oh yeah, the graphics really are fire. Let's see if I can, I'll take a picture and show it to you while you guys are thinking about this one. Let's see, how do I do this? I watched like this intro video where they were like just perusing through a city and you can like see like that. Hold up. So here's the screenshot right now. So that's kind of cool looking and stuff. That's what it looks like. Yeah. Should have bought this thing years ago. All right, anywho, A, B, C, or D, go. I see a not sure and a B from the same person. Well, that's interesting. See some A's, see some not sure, see some B's, see some not sure's. So B, not sure, but I want to say B. Well, P1 hat is the proportion of successes in my first sample. I had 61 successes over 103 is my sample. 61 over 103 is 0.592. 54 over 100. The proportion of successes in my second sample was 0.54. So P1 hat minus P2 hat is 0.592 minus 0.54. Correct answer is A. So explain, please. What to explain? Successes over trials. 61 over 103. That's P1 hats. 54 over 100. That's P2 hats. Subtract them. That's this. I'm not sure what to explain. I'm sorry. The formula for P1 hats is like before, successes over trials. I can't really go any deeper. Let's see. What's the formula? Successes divided by trials. 61 over 103. It's like if I shoot 100 baskets and I make 27 of them and I say, what's my proportion of successes? It's 27%, 27 over 100. Right? ¿Verdad? ¿Entiende? ¿Comprende? Do those mean the same thing? I don't know. Whatever. Is there a difference between them? Nobody? Nobody speaks whatever language? Okay. All right.
Comprende is understand, and what was the other one you said?
Entiende.
That comprende is to understand, and entiende is to listen or to, I guess in the subtext you use it, it could be to understand as well.
Oh, so they're synonymous in some sense. I don't know. I took Spanish in college. I got a C. So I retook it because I wanted to get a stronger foundation. And then I got a D the second time. And I said, screw this. I already know Hebrew. Why am I learning Spanish? So I didn't do that anymore. So who needs to know Spanish? The government and the birds are taking over. That's an interesting perspective. I don't quite agree with you. They've been planting cameras in the birds. They aren't real. This person needs help. All right, sampling distribution, the difference of sample proportions. The difference of sampling proportions. Okay, you take an SRS from both populations, an SRS from both populations. You have the average. This person needs okay. Quarantine is when they recharge the bird. Oh, I see. Okay, they recharge. Yeah, they keep us inside. They recharge the birds. Who knows? We can't go outside. We don't see any birds. I get it. I'm with you. Okay, I changed my mind. You're perfectly normal. Boop, boop. Okay, anyways. So we have the formula here, which is our standard error for this situation. It's P1 times 1 minus P1 over N1 times P2, sorry, plus P2, 1 minus P2 over N2. This is the one that we're going to use in our formulas. The only problem is, for confidence intervals at least, is that we do not know P1 and P2 before we actually take the sample. So when you don't know P1 and P2 before you take the sample, what do? Use P hats or use fats. I like both. Right? Someone said use fat, but I think he meant use P hat. Okay, so yes, this is a standard error. Okay, and here's the rule of thumb when you get to use it, right? We want n times p to be greater than or equal to 10 and n times 1 minus p. But in this case, we want them for both samples. We want it for sample 1 and sample 2. So not just one or the other, but both. And like before, we're going to be working under the assumption that we're dealing with a normal situation, which means that as the n's get larger, they're in the denominator. So as the n's get larger, we're going to have a narrower distribution, which is how we hone in on the true value. The center is P1 minus P2. Even though we don't know that, but we can still use the null hypothesis. And then we have our sampling distributions, which means if I take lots and lots and lots and lots of samples, they're going to be all over the place, but most of them are going to have their values congregate somewhere near the true value, and not a lot are going to be on the wings. How do we do it on Crunchit? Well, the same way. In Crunchit, well, I closed down Crunchit, but on Crunchit, you should see when you go to statistics, you're going to have Z, you're going to have T, and you're going to have proportion. So you're going to have 3 different sections for which you can choose either 1 sample or 2 sample, etc. So in this case, you're going to go to the proportion section and you're going to choose the 2 sample. And then you're going to plug everything. So what is the shape of the sampling distribution of P1 hat minus P2 hat for large sample sizes? For large sample sizes. So what's the answer going to be for large sample sizes? So B is good. It's approximately normal. It's never, you can never go and say it is normal. It's approximately normal. I don't know, he might say normal, but it's not exactly normal. It's approximately normal. There you go. So we know that 10% of men and 8% of women are left-handed. Oh, actually, I didn't know that, but that's interesting nonetheless. For a sample of 100 men and 200 women, the mean of the sampling distribution of P1 hat minus P2 hat is what? And the standard deviation of P1 hat minus P2 hat is what? So I'm going to give you a couple seconds to think about this one. As I, check Facebook and stuff. Oh, look, no messages. Okay. Usual. Nobody likes me. What can you do? What can you do? I'll go back to MySpace. I got all my friends there. So who here? So come on, A, B, C, D, go. Write it out. What do you think it is? So I got a bunch of A's. Definitely a B, someone said. Definitely a B. Ooh, definitely. Not just B, but definitely B. That's crazy talk. Some D's. Okay, well, let's think about it. The mean of P1 hat minus P2 hat is P1 minus P2. If P1 is 10%, P2 is 8%. So P1 minus P2 is 0.10 minus 0.08, and 0.10 minus 0.08 is either C or D. So A and B are out, even though someone said definitely B. So it's always nice when you're definitely, oh my God, that's what an amazing picture that is. So that's out. And then the question is, what's the standard deviation? And that's going to be P1, P2 over N1 plus P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. So the answer is D, which I don't think anyone said. Oh, hey, we got one. Yeah, we got one of the like 8 people who bothered to answer. All right, so confidence intervals we've already done. We're focusing this week on hypothesis testing, if you recall. So we did confidence intervals. Now we have hypothesis testing, which is important too. And if you remember the big difference between hypothesis testing and confidence intervals, the big difference was that for hypothesis testing, we use the assumption of the null hypothesis. Where, one second, someone said something. Where did 0.90 come from? Where do you see 0.90? Oh, 0.90? Well, this is 0.1, so 1 minus 0.1 is 0.9. All right. So for null hypotheses and stuff like that, we use the assumption of the null hypothesis that P1 minus P2 is 0, which is why we don't subtract P1 null, P1, P minus P2 or anything here because it's 0. This is our Z statistic. And because we're working under the assumption that P1 is equal to P2, we're actually going to use the pooled sample proportion. We don't look at P1 hat and P2 hat separately, but we pool them together. Why do we pool them together? Because we're working under the assumption that they're equal, and therefore we pool them, okay? But if the null hypothesis was anything other than this, if you had one of those rare situations where the null hypothesis was P1 minus P2 is 0.3 or something like that, then we would not use it, and we don't use it in confidence intervals. This is only in a slightly different test statistic for hypothesis testing. So in an SRS of 103 males and 100 female college students, 61 males and 54 females said they usually speed on interstate highways by 10 miles per hour or more. What is the pooled sample proportion P hat? The pooled sample proportion P hat, A, B, C, or D is what? Sorry, Professor, I have to leave. Okay, have fun. Or not fun, hope everything's okay. So what is the pooled formula? P hats, A, B, C, or D? I am so tired. Oh. Oh, wow. Okay. So, all right, good. Okay. Yeah, I'll take a nap when I'm dead. So I can't drink coffee. It's not in my diet. Plus, I hate coffee. It's disgusting. I just drink lots of water. All right. Cocaine is good too. So I've heard. So I've heard. Alleged. It's all alleged. That's what they say. Okay. So. Okay. Okay. So A, B, C, or D, guys, go for it. A, B, C, or D. So the answer is B. You add up the total number of successes, 61 plus 54, and you divide by the total number of trials, which is 103 plus 100. And that is the p hat, the pooled sample proportion. So just got to know how to use the formula. You plug it in here, you plug it in here. Other than that, it's all crunch it. It all comes down to crunch it. Uh-oh, saw the answers. So can't answer this one, but I'll do it anyways because people don't pay attention. We want to compare two populations and test whether proportion 1 is higher than proportion 2. What are the hey, look at you, got it right, amazing. What are the appropriate null hypotheses and alternative hypotheses? Well, we're comparing two proportions. The null hypothesis is always the equal sign, so B is automatically out. The hats are never in our null and alternative hypotheses, so D and E are automatically out. So it's either A or E. Well, do we want to see them be different or P1 greater? Well, that's what it says. It says greater, higher, so it's got to be C. And an SRS of 103 male and 100 female college students, okay, same thing. The test statistic is 0.75. That's what we got. Okay. For the null hypothesis, where the proportions are the same, versus the alternative that males have a higher proportion of speeders. The p-value is correct. The p-value is correct. The p-value is correct. I think they're asking what's the p-value. Well, I think that's asking what's their p-value. So what do we get? What's the p-value? Nature call. Be right back. All right, that's cool. That's cool. Nature call. What's the p-value? Anyone? Anyone? Definitely B. Well, I don't know. I can't do that in my head. Well, let's see. The test statistic is 0.75. That's on a right on a normal curve. So it sucks. On a normal curve, this one's even worse. On a normal curve, 0.7. Here's 0 at the center. Here's 1. So 0.75 is right here, and we want the probability of being past that. Well, 50% is to the right of 0. And we know 32% is to the right of 1. No, sorry, 16% is to the right of 1 because 68 in the middle, so 16 on the wings. So somewhere between 50% and 16%. And that leaves either B or C. And it's a lot closer to 1. So I would say it'd be closer to 16%. So I'm going to guess C. Oh, boom, shakalaka, yeah. Oh, and then reference slides. We don't need those. Okay. Okay, we get it. You know. Yeah, I love that celebration. So yeah, so okay. So that takes us to the end of chapter 23, and that should be which book are we using? We're not using that one. Do I have the book? Do we have the book? Oh, it's on sapling. That's right. It's on sapling. So hold on. Let me stop sharing for a second and load up sapling. That's on sapling. Okay, let's see where we're at. Let's see what more we have. Let's see what's going on here. Okay. Oops, no. Let's get that tab. Okay. Oh, actually, you know what I can do? I don't need this. I can do this here. So we just finished 623, which means we have 2 chapters to go, 6 and 25, which means we are way ahead of the curve because there's like 4 weeks left of the class, which means that we should have some time off for you guys just to do homework. Right? We should like learn nothing for like a week, but I can't like not have class because then I get fired. So here's what I'm going to do. Here's what I'm going to do. Not extra credit class. Here's what I'm going to do. I'm going to load up and make sure that all the homeworks up to 23. Well, so these ones you have till the 21st. I'm going to make 22 and 23 due in 2 weeks. 2 weeks from today, because we only have 2 chapters to go, so we don't have a lot more to do. Now there will be a test in there somewhere. I don't know what you know what? I do know what chapters it will cover. Hold on, because I have an email here. Hold on. The next test will cover 20, 21, 22, 23. Okay, the next class will cover 20, 21, 22, 23. That test will be 2 weeks from today. So here's what's going to happen for the next 2 weeks. I will log into class. I know the tests are harder. I know. Here's what's going to happen. I will log into class each Tuesday and Thursday because this is class time. I will not take attendance. And I will stay in class and I will do nothing but help people with homework. So for Tuesday, Thursday, Tuesday, the next 3, I will just do 20, or you can come and chill. That's cool too. Chill with the homie. Yeah, that's what I'm talking about. Or however you say it in this, you kids these days. So 20, 21, 22, and 23, those 4 chapters the next test will be on. It'll be next Thursday. Sorry, it'll be 2 Thursdays from today. And for the next 3 classes, because we're a little ahead, for the next 3 classes, I will just come into class from 4 to 5:40, Tuesday, Thursday, Tuesday, and to help on homework. Okay, so yeah, we won't learn anything new for the next 4 classes. That will still give us 2 weeks to do the last 2 chapters. Each one should only take a day. I think Thanksgiving's in there somewhere as well. In fact, when is Thanksgiving? It's not going to be my plans, is it? What's 2 weeks from today? 2 weeks. Huh?
Thanksgiving.
Is that 2 weeks from today?
I believe so, yeah.
I believe Thanksgiving is on the 26th and our exam would be on the 19th. So it's a week before Thanksgiving.
Oh, perfect. So we're good. So we're good. And those 2 chapters, I could probably even cover in a day because they're kind of connected. So this gives us 3 solid days to do the last 2 chapters. I think this is a wonderful plan. So that's what we're going to go for. What do you guys think? You guys like that plan? All right. So you don't have to come to class if you don't want to. No attendance will be taken for the next 3 classes, but I will be here. Can we go? You want to leave now? Wow. That hurts so much. I don't know how to take that. It's like you don't want to be here with me. But you know what? I'm going to be strong. I'm going to be strong. I'm going to pull through this. I can do it. I can do it. So I'm a little verklempt right now. So I'm hungry. I'm hungry too. Dad, I want dinner. Anyway, so yeah, we'll do that. Okay, so we're done for today. We finished chapter 23. I'm always hungry. That's my problem in life. So we are done for today. We're ready for the tests. It's just confidence intervals and proportions. Lots and lots of fun. Yeah. So that's it. No, it's not gonna make anything good. It's just the usual stuff, you know. Yeah, no, I'm kidding. He didn't really hear me because he's not upstairs. I just thought it'd be funny to do it that way. So, you know, I hope you agree it was funny because cucumber and salmon. Actually, I had a friend who caught a tuna, like a real tuna. Like she showed me a picture. It's like half the size of her, and she gave me a slab of it, and we put it in the freezer. So that's what I had yesterday. So it's not horrible. I must say, it's not horrible. It tastes like salmon, which is strange. I mean, why not just have salmon? But you know, so that's what I had. Potluck. Well, yeah, you never know what real. I mean, tuna fish. You know, you get it from the can. It's been processed and whatever they throw in there, but it's actual real tuna, and it tastes like salmon. That's really what it is. But anyways, I'm going to stop recording now, and